Please go ahead.
All right. Thank you for having me. Today's talk is about Mythic's technology and kind of how we think about compute and memory. And I'm just glad to be here. This is a very exciting technology space. And we see this being a dominant trend going forward for not just we're focused on neural networks, but we're actually seeing a lot of opportunities in other technology areas as well, where basically analog computing can be used as like a even for purely digital calculations can be used as a speculative computation technology, where you might need to be searching for an approximate solution, then you can confirm it with a pure digital technology. And so we see this as being, since it's so much more energy efficient, we see it as something that is going to become a mainstay component of the computer industry going forward. And it's just, there's going to need to be a lot of people working in this area in order to fulfill all the demand. So just excited to be here, and I'm glad we have so much interest in this type of technology. So Mythic was, just a little bit about us. Mythic was founded in 2012. This was right after AlexNet came out. There was a number of US Department of Defense calls for proposals around a brain computer. And our approach was to say, well, instead of creating subthreshold circuits that mimic brainwaves, why don't we create a computer out of analog components that's meant to accelerate AlexNet? And so we've been focused on, as a company, how do we approximate digital computation with analog components as sort of our mainstay? So instead of trying to develop new algorithms like with this the pulse-based computing and whatnot, we want to work with existing digital processes and existing digital algorithms and just try to accelerate them with analog computing. Since then, we've settled on a computer memory that uses Flash. We've hired about 140 people across Austin, Texas, and Redwood City, California, which is in the Silicon Valley area. And we raised $165 million in venture capital. Actually, when we first got started, I was talking to the Air Force, and they asked us when we would have a chip ready for sale. And I told them, we think it might take $10 million to bring a chip like this to market. It's very complex technology. And they balked at the cost. Like $10 million is astronomical. And $165 million later, we're like, oh, gee, like this is going to be tight getting to market on this. So yeah, bringing new technologies to market that, that haven't really been productized before. As we were talking about before the talk, there's a lot of nuts and bolts and details about how do you even define what good enough is for a technology like this. It takes a lot of time and a lot of brain power. So that it's been an exciting road over the last, I guess, 9 years now. And we're obviously sampling the customers now, so we're right at the finish line, and the finish line of this lap, I guess, and of course there's many more laps after this one. So a little bit more about our product. We've got a let's see if I can find a pointer here. We do a we actually rebranded from IPU to AMP. So this is analog matrix processor, and our current product is a PCI Express attached accelerator. And so there will be some Mythic AMP that's connected to a host SoC or CPU, and we connect it through PCI Express port. And our product doesn't have any DRAM or anything like that on it. So the host system will have its, various internet connect, or like radios, Ethernet, DRAM. There's a camera here and NAND flash. So the host has like the whole system, and all we're doing is accelerating the neural network applications through this PCI Express attached accelerator. And we're targeting these sort of applications where You can see this security camera. The around like 2 to 10 watt range is probably the market segment that we see the most advantage over traditional digital computing. Because if you're doing something under a watt, then the host SoC might have enough computation and capability to handle that. And if you're going to 30 watts to 50 watts, maybe you want to use like a NVIDIA or some other digital technology. But in the 2 to 10 watt range, there's not really that many digital products that can really compete well with analog computing in that space. So we use obviously matrix multiply calculations, and what we see is at least a 10x overall system efficiency versus digital systems. So taking not just the analog computing part, but if you have to look at the big picture of like, how do you get all the data to this place, and you have all these biasing circuits that in an academic setting you might have off chip, you have to bring them on chip, and how much space and energy do those take? So we use current-based calculations for our matrix multiplication. We use a DAC to perform this, to convert a digital value like an X0 to a V0, and we have that voltage across these resistors, and then those will generate currents. So and then those currents get digitized with an ADC back into a digital value. So our digital system architecture, or sorry, our system architecture is entirely digital. We only go into analog computing inside of a matrix multiply calculation. And then inside of that matrix multiply calculation, we do a DAC and an ADC, and we do our matrix multiply in the current domain. So just to give you an idea of the strategy that Mythic takes with analog computing. And for some applications, I'm also going to talk about GPS a little bit, which is where which was actually our first product or project. Sometimes we use SRAM or digital transistors to represent these values. For something like matrix multiplies for neural networks, we actually need a lot of values for this variable, or for this matrix element here. And then for that reason, we use flash transistors because we can vary the conductance. And that technology was chosen. We'd actually surveyed basically every non-volatile memory available in 2012 and 2013. And flash memory was at the time the only one that we saw as viable in the near future for this type of technology. Since then, there's been a lot of development in various memory technologies. I'd say that flash technology is still the only one that's product ready at the moment, or production ready. But we see a couple PCM and RRAM type things that are very close to being production worthy. So those are something that we're thinking about for the future. And of course, just finishing out the slide here, we're going to basically, by having these voltages across these word lines, and these bit lines are actually pinned to a known voltage. So it doesn't say that in the slide, but we're holding this to a particular voltage on these lines. That's going to generate these currents, and this gives us the matrix multiply calculation. So you have your current here is equal to V times conductance, and that'll give you current, and then you sum it up for all these components. And so we can actually do an entire matrix multiply in one shot. And so that's 250,000 calculations for the array size that we use. Being able to do 250,000 calculations on one array in parallel is a very powerful technology, but power efficient as well. Let's see. So if you look at the overall product, the way we run our system, and this is a key for our customers, is running batch size of 1. If you look at a lot of the digital technologies, even the ones that are targeting edge nominally, a lot of times in order to get energy efficiency, they have to run a larger batch size, maybe even like 30 or something like that. So batch size 1 is critical for many real world customer applications that we work with. And in particular, the single frame latency. So our latency is very small. It's basically 1 over the frame rate because we're only computing 1 frame at a time. The performance needs to be high. So from what we've seen in the market, you really want to be in the many tens of teramax or hundreds of teramax per second in order to have a competitive product. The really low performance stuff can be efficiently taken on with like subthreshold digital or something like that. So there's other technologies that can do low performance. We see a lot of benefit in high performance. The sort of the minimum threshold in energy efficiency we think is around 0.5 picojoule per Mac or 500 milliwatts per teramac. If you can exceed that, then you're basically in the gravy. And then we see advantages for analog compute or compute in memory for hyperscalability. So being able to scale the performance and the power together very proportionally is a key benefit. And of course, we have the boilerplate. We support all the different networks and all the different tooling. So this is what our current product looks like. We ended up with a grid-based design. And so if you look at these tiles, there's I didn't put on the new terminology here, but we have a matrix multiply tile here. You can see the custom unit is this big array at the top. And then we've got the RTL and SRAM for the rest of the tile there, and we end up putting it in the grid. The sector control tile here in the middle, so that's for biasing. So we need to generate analog biases for the, all the analog compute stuff. So that's where our band gap is and whatnot. And we need to have charge pumps for the flash memory. So that's one of the disadvantages of flash memory is it uses really high voltages instead of high IO voltages. And so in order to use flash memory, you have to have charge pumps, and we put that in the sector control tile as well. And so the sector kind of is this like long rectangular wedge, this horizontal wedge. And so all of the tiles in the sector share the biasing and charge pumps in that sector. And so one question I got at the beginning when we were working this is why not just have one shared across the entire chip? And there's kind of 2 reasons for that. One is when you're trying to verify the system, it's way better to when you have an analog component, the whole analog component basically needs to be simulated together. And so if you're sharing biasing and whatnot across the entire system at the same time, then your verification problem gets expanded to the entire system. And if you wanted to grow the system or make it smaller, it becomes more challenging as well. So by having a sector controller and this whole all being a sector limits the fan out of any of the analog circuits to one sector. And so if you want to add or remove computation, you can just chop off these sectors or add more sectors, that kind of thing. The interfaces are entirely digital at that point. So from a system scalability, system verification standpoint, limiting the scale of limiting how far analog signals go has a lot of advantages. In the bottom left corner here, we have our PCI Express and our chip control. Chip control has things like your PLL, your ROM for booting, and other ons and ends that you only need one of for an entire chip. And then the PCI Express port is of course our interface. So we just gonna chop off the bottom 4 tiles, and then I think this corner we filled with test structures and whatnot. So that kind of gives you an idea of how we constructed the system. So the overall, advantage here is, of course, that if you look at like comparing against a high performance GPU and a high performance SoC on a critical application like ResNet, we can basically keep the performance of the high performance GPU and just completely outstrip a high performance SoC. And then, but when we look at the power, our power is more similar to the high performance SoC. So you think of it like we get the performance of a GPU and the power of an SoC, and that's kind of our advantage. and so trying to push GPU performance in edge form factor is very appealing, of course, to a lot of companies trying to do real world products. I think one thing that doesn't quite, get talked a lot about is that, we have all these really interesting models out there in terms of, we get really high accuracy, and we're really pushing up the how capable these models are. But then if you go and try to actually run them in a real system, the difference between like the biggest NVIDIA GPU and what you can actually run in a $500 or $200 product is like orders of magnitude different. So of course that's where like tiny ML and whatnot came from, but we see a lot of need for high performance in this sort of like edge form factor space. And we actually see a lot of interest in open pose. Pose detection is a very practical application, at least compared to like classification. I think ResNet is a great backbone for a lot of other networks, but open pose is a full application, and this is one where we see a lot of advantages for our customers. Okay, so I'm going to kind of go through how we think about compute and memory, and kind of give an overview of, I'm probably going to skip through the analog compute overview because you guys already know that pretty well, but then go through the GPS and neural network applications. Okay, so this is how we think about like why people should use compute and memory. So, and if we look at traditional compute architectures, you typically have this style, especially for high performance, where you have this might be like an Intel chip or an AMD chip, where you have your CPU, and then you have various levels of caches. Those talk to DRAM, and then the DRAM talks to the SSD. And so if you think about like your virtual memory in the system, the virtual memory of the system might actually exceed the amount of DRAM that you have, and that of course exceeds all of these levels of caches that you have. So you're kind of you have your memory kind of spread out across these different areas where they each have a different latency for access and a different bandwidth. And so when we talk about compute and memory, it's kind of like relative. We use it at Mythic for a very particular application in a very particular way. But I think the idea is that if you think about compute and memory more broadly, it could actually exist in a lot of different places in the system. You can have compute memory inside of these caches. You can have compute memory in your DRAM chips, compute memory in your SSD. And so when we think about compute memory, we really think about just how can we bring computation to the memory itself for applications that are memory intensive. And we'll get into more detail what that means. So the memory structure I just showed with the caching system has kind of a lot of built-in assumptions around temporal locality. So if you look at like, so just a reminder what temporal locality means. It means that if you access a piece of memory, then the odds of you accessing it again are much higher. So there's correlation. Memory I'm using now is memory I'm probably going to use again in the near future, whereas memory I'm not using now is memory I'm not likely to use in the near future. So that correlation is one of the main things that that memory architecture is taking advantage of. Another one is spatial locality, and that says like if I access memory location X, then memory location X plus 1 is also very likely to be used. And so when we build these systems, we build in memory prefetchers and whatnot to bring all of that data together. So if I'm accessing memory location X, I go and find all of its friends nearby. And there's all sorts of different strategies for how to figure out what, when I access X, what other data am I going to access. And so these things are all also based on probability, but not certainty. So the entire architecture itself is speculative. We don't know what the memory access is going to be because we're running like a general program. And so we're just going to guess based on these correlations. And so those are all key elements of that style memory system. So one way you can analyze this kind of system is through something called a working set. And so the working set of memory is the amount of memory needed by the application over a period of time. And so this graph is kind of hard to grasp at first. And so we've got frequency of use. So how frequently am I using it? More frequently more frequently up here, and then less frequently down here. And then the amount of memory that we're accessing is on the y-axis. So I always get these axes messed up. But basically it says, if I look at a short period of time, there's very little memory that I actually need in a short period of time. And then if I look at the total amount of memory I'm going to need over the entire run, so maybe like frequency of use is just like once, that's going to be a lot of memory. And so we have this kind of this sort of access pattern where we need a ton of memory, we need a ton of memory overall, but only a tiny little bit of memory at any one time. And that kind of matches our cache architecture, right? So if you look at our like L1 cache, it's very tiny, but most memory hits in the L1 cache. We don't normally have to go up to L2 and very less frequently up to L3. So if you kind of draw those lines on here, you can kind of see that these lines are made up. So this isn't drawn from any particular thing, but you can see that, you know, the L1 cache is going to hit the vast majority of data accesses, and then all of those are going to fit inside the L1 cache, and so that's key. And then the L2 cache is going to capture an order of magnitude more, and then L3 cache is going to capture an order of magnitude more, and so on. So the idea here is that we very infrequently need to get out to like the SSD or the DRAM, but we can overflow into those when we need to. So where compute and memory, I think, makes a big impact is when we have different memory access patterns. So we showed here where the L1 cache is able to capture all of these memory accesses because we don't overflow into L2 cache land until here. And so the vast majority of the time we're able to do that. But if our access patterns look more like this, where we need a lot of data very frequently, then that's where we kind of, you know, get in trouble with the existing compute architecture, because basically we're going to be shuffling through all this data over and over and over again. And you can see that with neural networks where, you know, we have all these weights in the system, and every single frame that we compute, we have to cycle through all of the weights again. That gives us this style of access pattern. And if we exceed our L1 cache, then we're just constantly spinning through it. And the caches at that point become almost like a liability instead of a help, because now you're spending time with cache misses when you could just be streaming the data directly, since we know what the access pattern is. So we have some more. So these are some additional reasons for compute and memory. We've got deterministic data patterns. So we'll show in these applications we're looking at today. We know the exact data access pattern that we're going to perform. So these hierarchical memory systems don't provide a benefit and are in fact inefficient at that point. We know we have some ASIC capabilities that can further minimize data movement. So if we know what the data access patterns are going to be, and we know what the calculations are going to be, then we can build ASICs to kind of accelerate those things, so we don't need a general purpose computer. And then analog computation, which is of course what we specialize in. If we know a lot about the application and it's something that can accept the fuzziness of analog computation, then of course that's going to give us a huge benefit as well. So compute and memory, I think this is one thing I have to always make clear to people. Compute and memory is not always the answer to any problem. And so, you know, in general purpose computing, we don't have any aspect of the problem that we can actually take advantage of. So it becomes very difficult for us to use compute and memory in those applications, or at least I don't know how. maybe you guys have figured out how to do general purpose compute with this, but the way we think about it is we need to have some aspect of the problem that we're taking advantage of in order to make compute memory make sense. Low application importance is another reason to avoid compute memory. Typically, when we're using compute memory, it comes at a cost, right? It's increasing the system complexity. It's normally we always have to have like an SoC that has the standard memory hierarchy that we talked about earlier. So compute memory is going to be an addition on top of that. And so if your application isn't a huge part of your workload, then you quickly run the Amdahl's law, where maybe you're accelerating something that's not very important, and then that cost isn't worth the incremental cost of the system. And then small working sets. Typically, if you're using compute and memory, typically you're working on an application that uses a lot of memory and very frequently. So your high frequency working set is large. So if you're working on an application that can fit in an L1 cache, then compute memory probably isn't the way to go for the problem that you're trying to solve. So I'll just kind of go quickly through these slides. So analog computing is basically we're going to be using some sort of physical phenomenon in order to compute in a way that isn't going to give us binary numbers. It's going to give us something sort of like a floating point number in the end that has some fuzziness. And we see a lot of advantages from being able to reduce gate counts and wires. So if you look at a digital solution for addition versus analog solution for addition, there's just far fewer wires and components. And so if you reduce all the parasitics, in the end, that's all power and performance comes from, is all the parasitics in the system. So fewer wires, fewer components, less parasitics, so you can go faster and use less energy. There's different styles of analog compute, charge, conductance, current. We primarily use current and Mythic because we see that as being the most forgiving in terms of analog compute styles. And so maybe that's just what we've become comfortable with over the years, but that's the style that we like. So most of the problems that we're looking at are large matrix multiplies in the end. And so if the big comparison we can make is across these like giant carry save adder trees in order to do a digital multiply. And of course we can use current sources, which are implemented with like a single transistor or a pair of transistors. And then these currents just sum on individual wires, and then the addition is performed by connecting the wires together. So we see a lot of advantages for large matrix multiplies for doing these sorts of summations here. So some downsides, of course, we've got some noise, there's less flexibility, and then we've got some potential data corruption as running the system. So we have to have applications that can tolerate these things. And any sort of signal processing chain is, of course, excellent. So if your initial camera or initial data feed is from like a camera or a audio source, then those already have these problems. So your microphone already sucks, your camera already has dead pixels, etc. And so having a little bit of extra noise in your processing of that signal doesn't really change anything at that point. It just becomes more noise to your signal chain. The other thing, the other big philosophy that Mythic has is using analog where analog is best and using digital where digital is best. So I kind of mentioned this earlier, where we do a matrix multiply in analog, but the rest of the system is in digital. So things that digital is good at, memory storage, storing analog signals like we use SRAM, is very difficult. So we just convert data back to digital and store it in SRAM. SRAM is excellent. We don't see an analog way of reproducing SRAM efficiently. And then long distance communication, I showed that system with the grid of tiles. We have a network on chip there that communicates as well. So I'm going to go briefly through our experiences in GPS. This was the very first application that the Mythic worked in. And this was GPS is of course, you're trying to locate yourself in 4-dimensional space. So you have like your 3 spatial dimensions and then 1 time dimension. And so you need to get a lock on these 4 satellites. The way that you get that lock is each of these satellites is going to send some binary signal. So it's just going to be 1s and 0s. And the satellites are transmitting those signals under the noise floor of the atmosphere. So what you have to do is correlate these signals over a long period of time. And so you could think of it like this GPS signal is sent, the signal's under the noise floor, so you can't actually see it. So in order to find it, you have to basically do a correlation over a large number of bits, like thousands or hundreds of thousands or millions of bits. So they kind of line up the 2 signals, perform a dot product between them, and then see how strong of a match you get. The longer you make this pattern, the more it will reject noise and increase the gain. So this is very similar to neural networks in terms of calculation. We're doing dot products, except we're typically doing 1 dot product instead of hundreds. What we found also is that this is also very time and energy intensive. So in the civilian space, they actually have lots of tricks for how to bypass this process. Your local satellite, basically there's data caching. The local cell phone towers will actually cache information about like the satellite feeds and stuff like that. So you can short circuit the search. In the military space, and we were doing this for the Air Force, you have no such luck. And the signal doesn't repeat in the military space. So the civilian signal actually repeats. The military one does not. So that makes it even harder to search. So what they found was that soldiers in Afghanistan and Iraq would have these military GPS and they just wouldn't use them because it would take them like multiple minutes to get a GPS lock. And they'd use like a Garmin watch instead that uses the satellite or the civilian signals. So our goal was to accelerate that process so that the military GPS was actually usable enough for the soldiers to actually use it in the field. And so we use analog computing to perform this matrix multiply. And our circuit architecture looks something like this. For each, we're multiplying those thousands of bits together. And we basically have our patterns stored in an SRAM. And at each element of the SRAM, we have a current source that we can current steer positive or negative. And so we're going to shift in this pattern that we're getting from the satellite, and we're going to shift it to all these like SRAM bits. And depending on the correlation with the local pattern that we stored in the SRAM, that's going to do this current steering comparison. And we drop the current on these 2 lines. So just to recap again, we have the satellite, the expected pattern stored in SRAM. We have the signal that we received from our and our antenna that's being shifted into the SRAM as well. So the SRAM stores 2 elements, does a comparison, and then is going to output, is going to current steer either positive or negative. And then for current summation, you basically need to keep the bit lines at a known voltage because the current source is only going to produce the expected amount of current with the known with the specific voltage on these lines. So we have a basically 2-stage process for that. We have a common mode and then a differential mode. So the common mode is going to just try to equalize these wires so they're centered on our VREF. And then our differential mode is going to try to force those wires together. And when we do that, we have a resistor across here, and that's going to develop a voltage from the output of this op amp. And so by stabilizing these 2 wires at the target VREF voltages, we're going to develop a reference, a result here. And then we go through a sample hold and then an ADC. And so just briefly, we basically will test one time step, generate our result, test the next time step, generate the result, test the next time step, generate the result. So if you look at the system, we're kind of snaking this pattern through the SRAM, and it's just doing a shift and then a giant dot product, a small shift and a giant dot product. So this application is excellent for analog computing and compute in memory, because the amount of data movement is actually small, but the amount of computation is absolutely enormous. And so we found this to be very efficient. We developed a system with 4096 cells. We did it in TSMC 65. And this is an example of the calculation where we only had an 8-bit output, or sorry, a 3-bit output, but this is actually completely sufficient for GPS. And you can see that the analog computation very closely matched the digital computation here. But we were able to run this 100 times faster than what a digital system could for the same power. And so this was like a total game changer for acquiring those military satellite signals. We had some analysis that showed that the analog noise was actually far less than even the quantization noise of the digital of the ADC front end of the not our ADC, but the ADC of the antenna for the GPS signal. And so if again, you have to think about the problem as the total signal chain. The analog computation here was not adding any significant amount of noise to the signal chain in the system. And so if you looked at our work compared to previous systems, we were able to perform much higher levels of performance here than what previous systems were. Now you can see that like for TOPS per watt, there was another system from ISCIS that had a higher TOPS per watt for us, but the amount of TOPS that it could do is like minuscule. So having a system that can do a tiny amount of work in a lot of cases isn't that interesting in the real world. So being able to do both high energy efficiency and high TOPS is critical. So when we went to go and fundraise for Mythic, we found that the GPS market was actually not something that we could build a story around in terms of a business. So we ended up not actually pursuing this as a product, but luckily we had neural networks also in the works at the time. So this is the one that we fundraised on. And so the idea is the same as GPS. The two big differences were that we had, instead of one signal that we were trying to correlate at a time, we had several, and our values in these weights need to be higher. So before, I didn't really go into details, but we were storing 4-bit weights, or sorry, not 4-bit, 2-bit weights. And then here we're actually doing 8-bit weights. So going from 2 bits to 8 bits was a big difference. But if you look at the problem, a lot of the aspects are pretty similar in terms of how much information exists in the weights versus how much data movement does there need to be on the input data. And so this slide kind of breaks into the calculation where if you look at a matrix multiply for neural networks, you'll typically have these neuron weights, and then you'll have your input data and your output data. And so in this slide, I call this your weight data, and then your intermediate data. You could also call this activation data. So I think that's what's typically called. And so if you look at the size of these, for a given vector, you might have 1,000 inputs, 1,000 input activations, 1,000 output activations. But then if you multiply these together, you get like 1 million weights. And so the amount of data that's just sitting around in weight space is enormous. It's orders of magnitude more than your input and your output data. And so that's the thing that we can really take advantage of in our system. Going back to the earlier discussion about what can you take advantage of in the system to make compute memory worthwhile. The things that we can take advantage of here is a large working set. So we have this enormous number of weights that are kind of sitting around and they need to be accessed over and over and over again. And then the fact that the data movement for your activations is actually relatively small. So what we see in a lot of other systems is that this weight data is large enough that it actually ends up getting stored in DRAM. And then by doing that, every time you access your weights, you have to pay a DRAM access fee, which is extremely expensive. And so that's where that large batch size gets thrown in, is if you have a larger batch, then you can amortize the cost of accessing DRAM over each element in that batch. But since a lot of the applications we're looking at really want a batch size of 1, so you can't use that amortization. And so that's where compute memory basically can outperform. So if we look at deep neural networks, it's all about weight memory in terms of how do we build these applications. If you look at these different networks, you've got tens of millions of weights, and these are very difficult to fit in edge solutions. And since I made this slide, there's been more research into like things like efficient net and whatnot that try to reduce the total number of weights. But then a lot of times those networks add calculations that are also not acceptable for edge systems. So, like edge TPU won't run them. It's kind of funny, like Google made like an efficient network, but then it can't run on their edge platform. So they ended up making a TPU version of efficient net. And so that's where, basically this is difficult to get away with. We can try to improve, or difficult to get away from. We can try to improve the number of weights over time. And I see that being a trend. Of course, we want to improve the efficiency of our networks more and more over time. But at the end of the day, we're going to have many, many millions of weights. And that gets difficult to fit in the onboard memory of an edge system. We also typically have many millions or billions of max. And if you're running at 30 frames per second, which is typically the floor on many applications that we see when we talk to customers, then you're running in the billions or trillions of calculations per second. Now, a lot of systems use DRAM. There are some benefits of DRAM where you can fit some large models and you don't need quite as much SRAM in your system, but the cost of accessing DRAM is enormous. So we see DRAM as being something to be avoided. Now we do kind of expect to add DRAM to our systems at some point because it gives you that extra flexibility, but that's something where we might have it as something that would be kind of like an overflow to be rarely used, as opposed to something that we need to use for every stage of calculation. As soon as you use it for every stage of calculation, you're in a lot of trouble. So if you look at the design points of neural network accelerators, you basically have enterprise and you have edge, and you have with DRAM and without DRAM. So with DRAM and no DRAM. And so if you're building a system with in the enterprise space, these dies are huge. They're like the full reticle, extremely expensive, thousands of dollars. The amount of SRAM, if you're trying to do a no DRAM route, you're probably running hundreds of megabytes. But what that lets you do is if you can run an enterprise system with no DRAM, you have enough SRAM at this point that you can fit that whole model, and you can fit, a small batch of data to run through it. And so you might be running like 70 watts, but you can get pretty high efficiency on that. In the edge space, there's no way to fit like 100 plus megabytes of SRAM. And so if you want to run, in order to be an edge, you really have to be below 5 watts for most applications. So in order to fit, under say 5 megabytes of SRAM, this would be a lot of SRAM for an edge system. In order to fit under 5 megabytes and a few watts, then these networks typically use really high sparsity, very low precision. And so they get poor accuracy, but they're able to get like decent efficiency, like 5 picojoules per Mach type of efficiencies. So Where Mythic comes in, we're using, instead of DRAM and SRAM, we're using this non-volatile memory. We're able to fit a huge amount of memory for the NVM, and that allows us to fit in these power ranges, and it allows us to have excellent accuracy, high performance, and of course, good energy efficiency. We also do this currently in a 40 nanometer process, as opposed to these like smaller nodes that a lot of the newer systems need to go to. So this has, I don't see 40 nanometers being a huge advantage in itself, other than that this means that we have a lot of Moore's law available to us over the next few years. So we've got kind of like a reset in Moore's law is one way to think about it. We're back in 40, so we can work through the progression. We're currently working on our 28 nanometer product, and we're gonna keep working our way through these different nodes, and we're going to have a lot of that's going to give us a lot of legs over the years to make up a lot of, or improve more and more, and kind of widen our gap over digital systems. So kind of touching back onto what our flash-based computation, in case you're not familiar with flash transistors, these are transistors that have an extra floating gate inside of them. So if you look at one of these transistors, there's basically an extra conductor kind of floating between the gate and the channel, and that's going to act as like a floating capacitor. And so here's a better picture. So you've got your source and your drain. You've got this floating gate here. And so this is a capacitor now, where you can store charge, which basically becomes a voltage offset. You're creating a voltage offset on the threshold of this device. So by basically putting a high voltage across this, or putting a high voltage the other way, you can kind of change the voltage that you've stored in this. Change the charge, which changes the voltage that's stored in this floating gate. And that gives us this adjustable current source, which is kind of like changing the conductance of the device. And the way this works is we've got all of these flash cells kind of arranged on a single word line, or sorry, in a bit line. And then we've got all these word lines. So this is kind of flipped compared to the other pictures I've shown. So the bit line's going left to right, and the word lines are going vertically. And as we turn all of these devices on, that's going to generate a current on the bit line, which goes to the ADC, and the ADC will convert that back to digital computation. So we use each flash cell as a gated current source. So we're actually going to modulate these on and off based on our input. So all of these alpha 0 through 5 are going to be controlled by our input vector. And then this current here is going to be the value that gets digitized to our output vector. All of the currents in this line are obviously going to sum through Kirchhoff's current law. And so that's how we get our addition. So we get our multiplication at the cell level by modulating this cell on and off. And then we get our addition for somewhat free on this bit line. So we have our input vector. These are going to, this is how we're going to modulate these current sources. And then we have our weight matrix. And this is going to be how we store all of our values. And these are going to be the conductances that we have stored in those flash cells. So I kind of showed you this diagram earlier. Diagrams, of course, flipped from what I just showed you, but we're going to store those conductances on each of these cells by modulating the charge stored in the flash transistor, and then it's going to generate currents going vertically. So when we go and flesh that out to the rest of the system, we go and look at an individual. This is a tile here, so a single tile. Inside of this tile, we have a number of standard elements. So we have, this is a custom block, kind of like a SRAM, but we're going to have our weight storage, and then we're going to have a digital to analog, so our DAC, and then we're going to have our analog to digital, so our ADC. So the tile itself is entirely digital, and communication between the tiles is digital. And just inside of this custom block, we're going to be in the analog domain. So the other elements of the tile, we have a SRAM for storing data. So that's all the intermediate data. It's also like program code, that kind of thing. We have a RISC-V processor. This is basically just like a microsequencer. And then we've got a router that's going to communicate between the tiles so we can send data from one SRAM to another one. And then we have a SIMD engine for performing calculations that we can't do in analog. So things like addition of, like sometimes the calculation doesn't fit on one array. We have to add those two arrays together. And so we do that with the SIMD engine. We'll add those together. We also have the max pool operation is done on the SIMD engine. And so this is actually a very important part of our system, since we're not able to do every last calculation on the analog matrix multiply. Showed these earlier. So kind of trying to wrap up within an hour. So we've got our AMP overview again. So to recap, we've got our, we're targeting a batch size of 1 so we can have a single frame latency. This is critical to many applications. We've got high performance, so tens of teramax. A lot of AI, unless you're doing like keyword spotting, requires an extreme amount of performance. So trying to hit tens of teramax is important to many applications. And high energy efficiency above like 500 milliwatts per teramak. Efficiency, or I guess below 500 milliwatts per teramak is the correct term, or half a picojoule per mag. This is the kind of like the minimum threshold, of course, and then we want scalability. So in conclusion, what is possible with compute memory? We see more than a 10x improvement in energy efficiency. We see more than a 10x improvement in performance. And I'd say performance per dollar is maybe the way to express this. So if you look at, how much performance you can get for unit cost, you can get much higher out of analog compute memory. We see it as being application specific, so not every algorithm can benefit from compute memory, but we see a lot, I talked about GPS earlier. We see a lot of other applications where there's significant value to doing these, especially in signal processing and other sort of large scale processing applications. The thing that we typically want to look at is the working set. So if we look at an application, are we doing, these terms don't really make sense here, but is the working set that we're using large, where we have to frequently access a large amount of data. So you think of like our smallest loops inside of our calculation. If the smallest loops are working on tens of megabytes of data, then this is probably a compute memory application at that point. And then we also want to look at the importance of the algorithm to the system. So is our system using this as 90% of something? So obviously for neural networks, I mentioned that there's other calculations that we need to do, like max pool and whatnot. Those are a very small percentage of the overall calculations. It's the matrix multiply that's the 90%. And then GPS, there's other calculations that need to be performed as well, but well more than 90% is these giant time domain searches, which are ultimately dot products. And then finally, how predictable are our data patterns? So is this an algorithm that we know the exact data flow? And if it is, then we can kind of build that data flow in. You saw in the GPS system, I mentioned how we had that snaking signal pattern that we were kind of snaking through all the SRAM. So we know what that data pattern is. So we just built that that movement into the SRAM itself. And then for neural networks is a little more general purpose, but the same idea. If you look at how we sized all the buses and whatnot in the system, we were definitely taking advantage of the data patterns of neural networks. So we want to be very cognizant of data movement, because that typically, when we're looking at compute and memory, the whole goal of compute and memory is to minimize data movement. so we can, extract the efficiency and performance. And so we have to be very knowledgeable of what those data patterns are before we start working with them in a compute memory environment. So that wraps up my presentation. I think we have plenty of time for questions. And let's see here.
Excellent. Thanks a lot, Dave, for the very interesting talk. Let me stop the recording first.